Let's talk about C503 here. So, Fermat's little theorem shows that a to the p minus 1 mod p is 1. This is why this leads to something we used in the RSA, where you had this number phi, which is p minus 1 times q minus 1. If you take any number in a group and multiply and take it to the p minus 1 power, you get 1. That's why you're able to take things to a power and take it to whatever remaining power gets you to here, and that'll undo it, because it's going to amount to 1. So anyway, the point here is we can do it in Python. So we're going to test this condition. This is a way to find prime numbers. The point is, prime numbers have this property. So any number raised to a prime minus 1 will equal 1 mod p, so we can tell if a number is prime by using that. So if we put that in Colab here, we're going to take a random number, and you input the thing you want to test, and 5 times it will just try taking a random number A and seeing if this property is true. And if this property is true, it passed, and otherwise it fails. So if I run this, and I give it a prime number, yes. All right, if I give it a prime number like 11, then it passes. It tries random numbers, and it passed every time because it's a prime number. But if I run it and I give it a non-prime number, like 9, then it fails. So that's all it is, one mathematical way to find a prime number. And so now you can find even pretty big prime numbers. So if I run it and give it, say, 1,000, that's not prime, so they're going to fail. If I run it and give it 1,001, that's also not prime, but somewhere up here there's going to be a prime number. So let me go to my project here. 121 will pass. I will fail. All right, here's a number that's 1,024 bits long and is prime. And the point is, you could never try all the prime factors to test that number, but you can do this simple test. This simple test just involves doing one exponentiation modulus, and see, it can very quickly test it. So this is how you find prime numbers. You find a test like this, you run several passes, and now it's very likely to be prime. So that's how you do it. All right, and so now we can check the density of primes. We're going to calculate, this is the density of primes. The number of primes there are in the region of a number n is 1 over the natural log of n. That's the prime number theorem. And so we can calculate it here with this code. And this is something that very much surprised me. All of this would be impossible if prime numbers were hard to find. But they are not hard to find because really quite a lot of numbers are prime. So if I run this one, and I say 1,000, in the vicinity of 1,000, the density of primes is 0.0004, which is, that's 10 to the 1,000. Let me try something. If I put in 3, 10 to the 3 is 1,000. So there, 14% of the numbers are prime. But if I go to 10 to the 10, which is like 100 billion, then 4% of those numbers are prime. If I go to 1,000, which is bigger than any public key anybody is using, then there's still 4 in 10,000 numbers are prime. That's why I say you only have to try a few thousand guesses before you'll find a prime number, even when you're going to the biggest number you'll ever want to use. So that's the secret here. That's how any of it works. So there's a couple of challenges to find here using those tricks. But just to get you used to primes and how to find them. So let me stop this one.